Assalamualaikum warahmatullahi wabarakatuh. Good morning, Excellencies, distinguished guests, participants, ladies and gentlemen.
The Honorable, the first Vice Chancellor of Universitas Jenderal Sudirman, Profesor Dr. Insinyur Ahmad Sodik, MSc Agriculture.
The Honorable Dean of Faculty of Engineering, Universitas Jenderal Sudirman, Professor Dr. Engineering Suroso, STM Engineering.
Our keynote speakers and invited speakers.
Professor Balaji Rajagopalan from University of Colorado Boulder, USA.
Professor Silvio Ranise from Fondazione Bruno Kessler, Italy.
Dr. Rosli Omar from Universitas Tun Hussein on Malaysia.
Professor David P. Watling from University of Leeds, UK.
Dr. Insinyur Heru Dewanto, STMSc Engineering from Institution of Engineer, Indonesia.
Mr. Yanto, STMSc PhD from Universitas Jenderal Sudirman, Indonesia.
And also, presenters and participants of International Conference on Engineering, Technology, and Innovative Resources 2021.
Welcome to the International Conference on Engineering, Technology, and Innovative Researchers 2021 held by Faculty of Engineering, Universitas Jenderal Sudirman.
The International Conference on Engineering, Technology, and Innovative Resources 2021 with them, Sustainable Engineering and Technology for Reshaping Our Community, aims to communicate the results of research in the field of engineering to jointly contribute to society through innovative research.
This conference would offer a large number of invited lecturers from renowned speakers all over the country. All accepted paper will be published in the Journal of Visit Conference Series. Best Papers and Best Presenter Awards will be given for the papers judged to make the most significant contribution to the conference.
Excellencies, distinguished guests, participants, ladies and gentlemen, we would like to request you to all rise because we would like to commence this program by singing the national anthem of Republic of Indonesia, Indonesia Raya. Thank you, and kindly be seated. Excellencies, distinguished guests, participants, ladies and gentlemen, we are now going to listen to the welcome speech delivered by the Dean of Faculty of Engineering, Universitas Jenderal Sudirman, Professor Dr. Engineering Suroso, STM Engineering. Ladies and gentlemen, please welcome Professor Dr. Engineering Suroso, STM Engineering.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. The Honorable of Vice Rector of Academic, Jenderal Sudirman University, the Honorable of Distinguished Keynote Speakers, invitees, presenters, and all conference participants. Best wishes to all of us. Good morning and welcome to the third International Conference on Engineering, Technology and Innovative Research, ICETIR 2020 from Purbalingga City, Indonesia. The third International Conference on Engineering, Technology and Innovative Research is organized by Faculty of Engineering, Jenderal Sudirman University, Indonesia. This year, because of COVID-19 pandemic, the conference is held virtually on September 1st, 2021 from Purbalingga City, Indonesia. 6 distinguished scholars will start the session as keynote speakers. Professor Balaji Rajagopalan from University of Colorado, USA. Professor Silvio Ranise, Fondazione Bruno Kessler, Italy. Professor David Wetling from University of Leeds, UK. Associate Professor Dr. Rosli Omar from University Tun Hussein on Malaysia. Dr. Heru Dewanto, President of Institution of Engineers Indonesia, and Yanto PhD from Jenderal Sudirman University Indonesia. We are very grateful for them to share their knowledge and experience in this conference. It is our great pleasure to welcome all of the participants of this conference. This conference provides a forum for researchers, professionals, and students from various engineering backgrounds in the development of technology and innovative research in engineering field. The third ICETIR 2021 invites the scholars and encourages the researchers to submit high-quality manuscripts and papers to this conference. I do hope that this conference to be a valuable forum and a great chance to share and exchange of ideas and discussion on all aspects of engineering and technology fields for improving the quality and benefits of the researchers. I would like to thank our staff of Faculty of Engineering, Jenderal Sudirman University, and all university partners and organizers. They have been working very hard to organize this international conference. I also would like to thank all of the steering committees, technical program committees, reviewers, authors, session organizers, chairs, other volunteers, and participants. At last, I wish you all enjoying the conference. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Excellencies, participants, ladies and gentlemen, we are now going to listen to the welcome speech delivered by the Vice Chancellor of Universitas Jenderal Sudirman, Professor Dr. Insinyur Ahmad Sodik, MSc Agriculture. Ladies and gentlemen, please welcome Professor Dr. Insinyur Ahmad Sodik.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Distinguished guest, keynote speaker, Professor Balaji Rajagalo from University of Colorado, USA. Associate Professor Rosli Omar from University Tun Hussein on Malaysia. Associate Professor Yanto, Jenderal Sudirman University. Dr. Heru Dewanto, President of Indonesia Engineer Association. Professor David Wetling from Leeds University, UK. Professor Silvio Ranise for Fondazione Bruno Kessler, Italy. Dean of the Faculty of Engineering, Professor Suroso, invite speakers, presenter, and ladies and gentlemen. Best wish to all of us. First of all, on behalf of Jenderal Sudirman University, I would like to welcome all of the speaker participants who attend the third International Conference of Engineering, Technology, Innovative Research 2021, organized by the Faculty of Engineering, University Jenderal Sudirman, in collaboration with the Faculty of Engineering Gajah Mada University, Universitas Indonesia, Universitas 11 Maret, Universitas Mula Warman, Universitas Hasanuddin, Universitas Palangkaraya, and Universitas Jember, and also the Faculty of Marine Technology, Institut Teknologi Surabaya, Faculty of Military Engineering, University Pertahanan Republik Indonesia, Faculty of Telecommunication and Electrical Engineering, Institut Teknologi Purwokerto, and also Faculty of Computer Science, Universitas Amikom. We also would like to thank to College of Engineering Technology Kento University, Vietnam National Center for Research ICETIR Engineering Taiwan, Faculty of Electrical and Electronic Engineering from University Tun Hussein on Malaysia. Ladies and gentlemen, shortly, work environment are expected to feature more use information and communication technology, more autonomy, less routine, reduce physical efforts, and increase social and intellectual tasks. During COVID-19 pandemic, most workplaces in 2020 to 2021 are also experiencing the effect. Engineers and scientists will have to contribute to new economic and societal challenges after pandemic smartly. As engineers and our students, we should be able to optimally and effectively deal with complex issues and make decisions instantly in professional situations characterized by uncertain, high level of risk and complexity. Jenderal Sudirman University has a long experience in engineering and technology research, education, and community service. As a higher education institution, Jenderal Sudirman aspires to produce qualified graduate or young engineer with significant professional knowledge, innovative idea, high attitude, and excellent leadership skill to respond to technology, economic, and social challenge. In Society 5.0, engineers are expected to have proper skill to turn product of the imagination into real-world innovation. Engineering grows with the influence of an increased humanity, knowledge, and need. This means that the future will be full of new opportunity of engineers. Therefore, University Jenderal Sudirman is deeply intends to support the scientific communication to provide solutions in respecting our community, including in the case technology and engineering aspect towards more society 5.0. I appreciate the program organized by the Faculty of Engineering of University Jenderal Sudirman and all of co-hosts. I hope this conference produce useful output, particularly in engineering to contribute to human well-being through the joint innovation research. I also would like to congratulate all delegates at the conference. May Allah Subhanahu wa Ta'ala always remind to us improve our knowledge, innovation for our future generation. Amin ya Rabbal Alamin. With name of Allah Subhanahu wa Ta'ala, Bismillahirrahmanirrahim. the International Conference on Engineering, Technology, and Innovation Research, conducted by Faculty of Engineering Universitas Jenderal Sudirman, is officially open. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Dr. Insinyur Ahmad Sodik, MSc Agriculture. Ladies and gentlemen, we are now continuing our meeting to the next agenda, that is to hear the keynote speech of the first panel session from our keynote speakers. Professor Balaji Rajagopalan from University of Colorado Boulder, USA. Associate Professor Rosli Omar from Universitas Tun Hussein on Malaysia. Assistant Professor Yanto PhD from Universitas Jenderal Sudirman, Indonesia. This session will be guided by moderator Dr. Engineering Purwanto Bekti Santoso STMT from Civil Engineering of Universitas Jenderal Sudirman. Ladies and gentlemen, please welcome our keynote speakers and moderator.
Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, welcome to the first session of Keynote Speaker International Conference on Engineering, Technology and Innovative Research. I am Purwanto Bekti Santoso. It is my pleasure to be the moderator of this session. In this session, we have 3 keynote speakers. First keynote speaker is Professor Balaji Rajagopalan from Colorado University, United States. The second keynote speaker is Associate Professor Rosli Omar from University Tun Hussein On, Malaysia. And the third keynote speaker is Assistant Professor Yanto from Jenderal Sudirman University. Each speaker will have around 25 minutes of presentation. All participants who have any question for the presenter, please use the chat feature in the Zoom. The question will be answered by the presenter at the Q&A session at the end of the session. Ladies and gentlemen, before we continue to the first presentation, I would like to introduce you our first keynote speaker. Professor Balaji Rajagopalan graduated bachelor degree in civil engineering from National Institute of Technology, Kurukshetra, India in 1989. He received master degree in quality, reliability and operation research, Indian Statistical Institute, Calcutta, India in 1991. He received his PhD in civil engineering, stochastic hydroclimatology, water resources from Utah State University, USA. Professor Balaji currently in the chair, Department of Civil Engineering, Environmental and Architectural Engineering, University of Colorado, USA. He received many honors and awards. The most recent is Fellow of American Geophysical Union in 2018. His research interest is mainly in stochastic hydrology and hydroclimatology, non-parametric functional estimation techniques, and others. Please welcome Professor Balaji Rajagopalan. Time is yours.
Thank you very much for the warm introduction. Can you hear me? Somebody can respond if you can hear me.
Balaji, it's clear.
Okay, thank you. Yeah, I will share my screen now.
Okay.
So then, can you see my screen?
Yes.
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 Please.
Yes.
Okay. Full screen mode or? Can you see the full screen or only the part?
Now, yes, sir.
Presentation mode.
So,
Okay, presentation mode.
Yes.
Okay.
Okay.
Okay, thank you very much. Once again, thank you for the warm welcome. I wish I was there in person. I'm coming from Boulder, Colorado. It's 7:30 here, Tuesday evening. So you are already in Wednesday. So I'm talking to you from the past, and that's as you will see from my talk, it is going to be consistent with what I'm going to present today to you. So, as was mentioned, I'm in the Department of Civil, Environmental, and Architectural Engineering, and my degree is in engineering. But what you will see from my presentation will be quite different from what you typically see in civil engineering. So, what I'm going to talk to you today is about a story of how climate was in the past, actually in the area not very far from where you all are living, which is the tropical Pacific Ocean, and also the Indian monsoon or rainfall over India. What does this mean for past and future civilizations? And it's very important now with lots of changes in climate extremes. This is a very important and very fascinating topic. So you will see that this requires engineering, statistical, climate, multidisciplinary. So let's get started. So this is labor of love that I've been working on for the past, I want to say maybe 8 or 9 years. And Yanto knows Emily. Emily Gill is the was my PhD student and postdoc. She opened with Yanto when Yanto was doing his PhD here. And then my excellent colleague, Peter Molnar, he is one of the leading geoclimatologists in the world. And then other collaborators. So I want to start with this picture where you'll see the, all of world's civilizations. Should I? Is it better now? Hello?
Hello.
Is this is the slide better now?
It is, sir, still shown.
We are still seeing your first pic.
Oh, you're only seeing the first slide?
Yes, Prof.
Yes.
Okay. Let me, thank you. So,
Yeah, it's already in the presentation mode now.
okay, so let me share and then you can. Okay, I think you should be able to see now.
Okay.
Okay, the first screen, first slide. Second, and so I was.
Like two.
Okay. Okay, I think it's good now. Can someone tell me it's good?
Okay.
Yes.
Yeah, it's perfect, Prof.
Thank you.
Good.
Thank you. Sorry about that. Yeah. So, is that all the civilizations started or flourished along major rivers, right? So what you're seeing here is the Mesopotamian civilization here in the Middle East, the Indian civilization, which I'm going to talk about in the northwest parts of the Indian subcontinent, and several others. You might want to mute the microphone. I'm getting an echo. So, Yeah, thank you. And most of these societies, most of these old civilizations are agrarian, so that means depending on largely on hydroclimate. Okay. And many of them flourished during this time period, 3 to 6 million, sort of the mid-Holocene, as it is called. Here is a picture showing how the civilizations rose and fell. And notice that all these major civilizations disappeared or climbed following major climate events. The Indus, for example, there was a shift in monsoon rains, which I'm going to talk about. Then civilizations elsewhere, you had a dry period, extended drought, mostly drought, extended dry period, which then moved all of this civilizations down. So clearly there is a connection between climate variability and then the rise and fall of societies. Okay. And this picture shows sort of the timeline, major events from 0 to 11,000 years ago. So x-axis is time, thousands of years past, and then the various epoch events, as you can see, and again, coinciding with the droughts, you can see the various civilizations that kind of declined. If you look at the Indus civilization, that's the one that I'm going to talk about. The Indus civilization is one of the oldest in India, which is what is modern day Pakistan, Northwest India. Notice that during the early period, 5,000 years before present, this was the Indus civilization, and then mature period is 4,600 to 3,900, and then when you get to the 3,000, it kind of appears. So 3,300 years before present is roughly 1,000 years BC or 1300 BC. So very, not that far, very recent. And notice that what was at the height, extending all the way from modern day Pakistan, Northwest India, and Western India to just some pockets. Okay. So the question is, what happened? Why did this civilization that flourished in this mature period, 4,600 to 3,900, almost, we are talking 1,000 plus years, suddenly just went away? Okay. So it's an interesting question. Why? So why was the decline? And also notice that the Indus civilization moved east. Okay. So why was the decline? And why did it move east? So that's the question we want to answer. And let me add everything so you can see. So as I said, I'm going to tell you a story. So of course, we all know for story, you need to have a plot. You need to have a story. That's what is called a plot. You need to have a hero in the story. And then you need some villains, right? So that's typical of a lot of our movies from that part of the world, or any part of the world for that matter. So as I mentioned, the decline is due to rainfall, because that's a good suspect, right? Because all these societies depended on agriculture, and when rainfall declines, they leave. So the hero here is the monsoon rainfall. I'll give you a very quick overview. And there are some suspects. What happened to that rainfall? So these are some suspects: land warming during mid-Holocene time, and then tropical Pacific, where you guys are all living. Okay. In fact, where you are living is one of the most important regions, climatologically important region of the world. In fact, my advisor used to tell, if you want to play God and change the weather and climate over the entire world, all you have to do is mess with Western Pacific sea surface temperature, which is temperatures that is around surrounding Java, all of the Indonesian islands, basically. Okay, so we have suspects, we have to do some investigation, obviously, and then we find out what happened. And we put some evidence or hypothesis. Okay, so that's going to be the plot. So it's like a story. So again, okay, so early to mid Holocene, Northwest India, lot of evidence that India was wetter. So there were a lot of these lakes, which are modern day lakes. In fact, now if you go there, it's desert. This is modern day desert over India, this Northwest India, but during mid Holocene, we 3,000 to 5,000 years before present, there is a lot of paleo evidence that that region was very wet. So lots of paleoclimatic evidence. This is to show that that period was sediments from lakes, sediments from the ocean, all of them pointing towards a wetter India during that time. So that's basically what you're seeing. And then afterwards, a gentle decline, 2000 by the time you get to modern times. And you can see all the various phases, the mature phase, the early, late phase, the Harappan civilization. Okay. Also from lakes, people have shown that India was better. So paleo evidence, strong monsoon during mid-Holocene. One thing I want to point out is, and we'll come back to this in a second, when you go back in time, there's no thermometer, there's no rainfall data. Right now we have rain gauges all over the place. We can measure how much it rained. Maybe we can go back to 50, maybe 100 years. You go to any part of the world, many parts of the US, probably 100 years. If you want to say anything about climate before 100 years, before instrumental, you have to do a lot of detective work. That's why it's fascinating, it's interesting. And because you don't know a lot of things, you have some evidence, and then you want to put things together with knowledge from other disciplines. So that is very, very important. Going forward these days, the most exciting problems are all in the interface of multiple disciplines. So gone are the days where I'm civil engineer, I'm just going to build buildings. No, you need to know water, you need to know environment, you need to know climate. So to the students in the audience, be very curious and be eager to learn lots of things, be like a sponge. Okay, so there's paleo evidence, and I'll talk about a little bit about the paleo data, what kind of data. Yeah. So in the summer of 2014, I went to, in one of my trips to India, North India, I went to Rajasthan, which is the Northwest India, modern day Northwest India. It's desert. This is how it looks. It's all dry, barren, sand. This is salt, it's not ocean. And you can see it's pretty dry now. But 5,000 years ago, this part was very wet. And there is a lot of evidence for that. Okay, monsoon. I'm not going to give a lecture on monsoon. You are all very familiar with monsoon. Monsoon brings, the rains always bring a lot of good memories. And then it also brings a lot of destruction and bad memories. Some years are really wet, some years are dry, and in between. And then even in dry years, you can get big extremes, and then you get destruction. Right? So I have fond memories of rainfall myself as a young boy, playing in the water with paper boats. I'm sure all of you in the audience and the students also have very similar fond memories. So what's monsoon? Basically, it's a land-ocean gradient, temperature gradient. So all of you are very familiar. If you are on the ocean, on the coast, during nighttime, during daytime, what happens? Land is warmer than the ocean, air rises, and then cooler air from the ocean or sea comes onto the land. And then in the nighttime, land gets cooler, and then the winds reverse. So this change in wind is what is known as monsoon. Also, Arabic word is mausam or mausim, simply means season. Okay, so it's change. So hot land and cool ocean, if you have, you get monsoon. And Edmund Hillary of the comet fame was the first to recognize way back and gave it the name monsoon. Okay. If you take this, what is happening on the coast, which I'm sure you all have seen, now you take it over the larger region, suddenly you get monsoon over much bigger region. Okay. And generally this happens, this kind of contrast is usually there in summer, right? Summer is when the land is hot, and then you have the temperature gradient. So if you look around the world, this is the map of the world. What do you need for strong monsoon? A lot of land in the tropics, because remember, you need a hot land. So that means a lot of land should be in the tropical region, equatorial region. A lot of water around so that you can get that contrast. So if you look around, not many places have both. For example, if you're in Africa, there's a lot of land, but then there's only very little ocean around. Okay. If you look at North America, same thing, southern part of the North America, there's land, but then the ocean is far away. Okay. So interestingly, the only place where there is all of this ingredient is the Indian subcontinent. Notice here, you have India, a lot of land in the tropics, there's a lot of water around. And so that's why Indian monsoon is really unique among all the climate systems in the world. So here is the monsoon system, Australian monsoon complex, as they call it. But there are 2 or 3 different monsoons. There's the Indian monsoon, which is the biggest and the most strong. And then there is East Asian monsoon. And then there's Australian monsoon, but they're all, smaller in comparison to the Indian monsoon. There's African monsoon, and then the American or the North American, South American monsoon. But in general, whenever you have this difference in gradient, it's monsoon, and a third of global population lives in monsoon regions, and therefore it's very important that we understand and study monsoon. Remember, in the monsoon definition, wind has to change direction. Only in India or the Indian region, the winds change 180 degrees. Nowhere in the world, the winds change completely 180 degrees and stays that way for a season. So here on the right side, you can see during January, winds are blowing from land and they blow onto the ocean. They blow from India to Bay of Bengal, Arabian Sea. And then in July, completely reverse. Winds are blowing from Arabian Sea, Bay of Bengal onto the land. Okay, this change in wind direction is very unique to Indian region, and therefore the Indian subcontinent is extremely, the Indian subcontinent monsoon is very important. Civilizations have used the monsoon for centuries. Trade routes from Middle East all the way to Indonesia, and then onto East Asia and China. Trade, ideas, religion, all of them used these winds. And it's fascinating, right? In fact, much of Islam movement into Indonesia happened with these trade winds, with these monsoonal winds. There was back and forth trade of ideas, of spices, you name it. Right? Of course, much later, the Europeans came and also used the monsoonal winds to do trade and so forth. So it's very fascinating. There are beautiful books about this, and you can see how ideas move. So it's almost like the Silk Route of the ocean, or the Silk Road of the seas. We have the Silk Road here between Central Asia and China and Europe. this is almost like the Silk Road of the oceans. This is a quick schematic of the Indian monsoon. As you can see, Himalayas are here. That's the land. And it gets hot before the summer season, which is June, July, August is summer. During March, April, May, it is hot over India. In fact, the Indian summer, as they call it, I'm sure you guys are all familiar. It's really, really hot during March, April, May. Air is rising, and then the ocean is cooler, still cooler from the previous winter. That gradient is what brings the monsoon. So the yellow is the moisture. So it blows all the way, dumps a lot of rain at the foothills of the Himalayas. You get a lot of rain there, and then air rises, that's the blue. And where it sinks, you get very dry climate, and the sinking happens over Afghanistan, over Saudi Arabia. So that's why those regions are all dry and desert, right? So if you have sinking, you're not going to get much rain, right? So there's a lot of convection in and around Indonesia. That's why Indonesian islands are always wet and green, right? And this is the rainfall distribution over India. I'm going to go scroll through. And there's a lot of data thanks to the British. And notice that the monsoon is pretty stable. There's some variability, okay? But it's largely stable. It rains during summer because the winds shift. Remember, this is the only place where the winds shift 180 degrees. That means it's going to rain. Now, of course, some year it rains less, some year it rains more, but it will rain every year. And that reversal of wind makes it. So what changes year to year? That's important. And one of the main dominant, notice that this is in recent times, it's declining. So that's a different issue. I'm not going to go over. And this is temperature here, also increasing just like everywhere else. Okay. And monsoon has a long history. The British have been studying the monsoon since they were ruling India. From the 1800s, 1884, Blandford, Walker, Sir Gilbert Walker, pictured here, he started the Indian Meteorological Department in Pune in 1928. And he's also was the one who identified this Walker circulation. And Tibetan Plateau is another, which is the land ocean part. And so these are sort of broad variables that drive monsoon rainfall from year to year. So some years are wet because you have less snow cover over Himalayas. But the big driver is the El Nino Southern Oscillation. So here is the monsoon, and here is the Tibetan Plateau and Himalayas. So when you have less snow here in the top left during the winter, that means when the summer comes, a lot of heat is going towards heating the atmosphere and the land. So you create a strong gradient, stronger monsoon, and vice versa when you have a lot of snow in the winter. And this Blandford, one of the British scientists, identified in 1884. Okay. That's the Tibet argument. The other is the El Nino. I'm not going to go over because I'm sure you all are very familiar with El Nino because here is Indonesia and the Western Pacific warm pool. This is normal conditions. Occasionally, the warm pool gets pulled out east, like here, and the Walker circulation also moves. So which means Indonesia gets dry. If Indonesia is dry, India is also dry. And remember, whenever there is El Nino, Indonesia gets a lot of those forest fires and so forth. That is also the time when India gets dry. The Indian monsoon is also weaker, okay, because you have the subsidence limb of the Walker circulation. So it's a good relationship. This is the temperatures over the tropical Pacific. Notice that if the temperatures increases, that means El Nino, rainfall decreases on the y-axis. If temperature is decreasing, which is La Nina, you get high rainfall. So cooler, if this Central and Eastern Pacific is cooler, more rain over India. If it's warmer, less rain over India. Okay, so that's well-known relationship that Walker identified and then subsequently people. And if you look at La Nina in particular, that whenever there is a 1 degree change in the temperature, cooling, then you can see that the green means there is increase in rainfall. So in fact, in some parts of Northwest India, you get 60–80% increase in rainfall for 1 degree change or 1 degree cooling in Central Pacific. So this is very important. Okay. So this is all based on modern day last 100 years. Again, I'm giving you like a very quick, like a 5-minute overview of monsoon. What should be, you can go like a full semester on this. Okay. Why is mid-Holocene important? That 5,000 years ago, mid-Holocene, because the Earth's orbit, which is tilted 22.5 degrees, wobbles. It's not always at 22.5. It kind of goes, wobble, and there is a cycle to that, and it's called the precession cycle. And so what happens is, during mid-Holocene, notice that the Earth is tilted, so the tilt happens to be closer to the northern hemisphere. Tilt happens to be more close to the sun relative to the southern hemisphere. And then during the other side of the cycle, the southern hemisphere is tilted to the sun, northern hemisphere is moved away from the sun. So what does that mean? If the northern hemisphere is tilted towards the sun more, you're going to get more solar radiation. That means northern hemisphere land is going to warm more. So if that warms more, it's going to increase the land ocean gradient, and therefore you get more rain. So that's basically the argument. And by the way, mid-Holocene is also somewhat like an analog to a warmer world that we are likely to experience. Okay. So that is one of the big idea that people have. Insolation increases. Insolation is solar radiation increases over northern hemisphere. That means land ocean thermal gradient increases. Stronger the gradient, more rainfall. So this is what the ITCZ, which is what that brings the rain. And so the ITCZ moves north, and therefore it rains. So this has been like the received wisdom. People, you pick up any paper in paleoclimate that describes why India was wetter, or parts of subcontinent were wetter, they'll just say, oh, land ocean gradient during mid-Holocene. Well, there's only one problem. Notice that in recent times, temperature is increasing over India and a lot of the land, but notice what is happening to the rainfall, which is decreasing. So that doesn't seem to work. And that is what got us motivated, there has to be another explanation. You cannot simply heat the land and expect more rain. If so, then currently large parts of the world should be getting tons of rain. That's not what is happening. Okay. So let's look at paleoclimate data. These are sediment cores. And when you look at sediment cores, what the evidence is that Eastern Pacific or tropical Pacific was much cooler. Okay, remember, cooler means La Nina. La Nina means more rain over India. So that is what got us in. Maybe there's something here. Maybe there's more than just heating the land. Okay, I'm going to go a little faster here. So all the proxy records, these are people going and doing sediment cores, deep ocean cores, and they find, and then they calibrate ocean temperatures based on the sediment cores and isotope analysis. And all of them show cooler Eastern Pacific. Okay. Cooler Eastern and Central means La Nina conditions. So during mid-Holocene, the Pacific was La Nina-like conditions, and the land was also warmer. So you can see that they both might be, that's why I call it suspect number 2. Suspect 1 is just heat the land because of the precession. Suspect 2 is, cooler Eastern Pacific. And as we know, if the Pacific is cooler here, then if the Pacific is cooler, then you get more rain. Okay, so we got to do the investigations. These are 3, detectives from past television serial. The left one is one of the detectives in serial from India when I was growing up. And this is, of course, the famous Colombo. And then there you see Sherlock Holmes on the right. Okay, so we got to do some investigation. We have these 2 suspects. Which one it is? Okay, so this is climate data or paleo data. Notice that they go into the ocean like this, and then they drill. And so they go into the ocean floor and drill, and then pull out a core. And when they pull out, this is how the core looks. Notice that there are layers of sediments, right? So these are sediments that are flowing from the land. by rivers and others. They flow in, get into the ocean, float. Next year, you get more sediment, they go on top and so forth. So each layer is compacted. The only thing is they don't have a clear sort of timeline like tree rings, but still you get these bands and you take sediment from each band, then you do isotope analysis, magnesium, calcium. The ratio gives you directly a relationship to temperature. Or you can also do what are known as alkanones. These are, these are like microorganisms that grow, and they grow under different conditions, typically cooler waters they grow. So you can take each sediment and look for these microbes, the shells, and then that also gives them, and these are called planktons, foraminifera. So those are typically the two paleoclimate studies data for past climate. And these cores, by the way, can go up to millions of years. Okay, I'll show at the end. So we have excellent sediment cores, and this is an international effort to drill these cores, and then all the data is available, but any of you can go online and select all of them. So we got this data set, these cores in the tropical Pacific. Notice that, of course, there's quite a few near the Indonesian area because a lot more data near the continents, near the land, because the ships can drill. You cannot drill in the central Pacific where there is, it's really deep. So sediment just gets dissolved. But still, a lot of them are on the continental shelf. So we have all this. Then this is the paper we want to look at, Gill et al. 2016 paleoceanography. So I'm not going to go into any detail. So we took this data and we used multivariate statistical techniques. And what we said is, let us take this individual location data and try to reconstruct temperature over the entire tropical Pacific. So we did that. So I'm going to scroll through all of this. You can read up on this methods in that paper. It's very straightforward, and I'll be happy to engage. And in fact, Deonto can also explain. He did use some of these techniques himself. So let me go through directly to the reconstructions, and here it is. So notice that what you're seeing here is the sea surface temperatures in the top. 2,000 years, 4, 6, 8, and 10,000. Notice that as you go to up to 8, 6, Eastern Pacific is cooler and cooler, but when you get to 2,000, the cooler temperatures reduce, right? And similarly, you can also reconstruct the winds. As you can see, if you have cooler temperatures, you have stronger winds, as you would expect. We can also use these temperatures to then reconstruct rainfall over India, which we did. So again, that's in a companion paper. That's Gill et al. 2017 paleoceanography. You can look it up. And I'll go directly to the rainfall over India. And so here it is. In fact, yeah. So notice that different parts of the country, particularly Northwest India, that is Rajasthan. Notice that as you go back in time, this is percentage change. In fact, when you're in the 4,000 to 5,000 years, that's when the Indus civilization was at its peak. You had about close to 30 to 40% increase in rainfall, and even at some places close to 50%, right? That's very, very interesting. Even North India, you see there is increasing in rainfall. Okay, so basically, the reconstruction are just using tropical Pacific data. And we also did modeling of lakes. We use simple hydrologic models, the kind that you would learn in your hydrology courses. And we modeled these lakes, and we found that to get a lake of about 5 meters, which is what they were, about 6 meter lake, you only need about 50% increase in rainfall, which we already have here just from tropical Pacific. So then another interesting thing, which is very recent, is this is the reconstruction of wind over Oman coast, because that's where the monsoon winds take a shift. And in olden days, Magan is what was called, Magan is the region here, Dilmun, and the Indus. So there was Indus is Meluha. So there was a lot of trade between this part, this region and this region over Indus, Meluha and Magan, Mesopotamia, Middle East. And it's well documented. And I work with a anthropologist, Adam Schneider, as the guy in the picture you saw at the beginning. And he said, hey, as the rainfall is decreasing, around this time, there was an increase in trade. And so this blue line is the wind over Oman coast. So yeah, it's declining, meaning less rainfall. And then suddenly for a brief period, there is increase before declining further. And so the Indus civilization starts to collapse somewhere around here, and then it went away. Okay, so I won't go through this, and in fact, I'll quickly wind up here. Basically, interesting things about how as the Indus was declining here, they couldn't grow crops, so they were exporting grains from Mesopotamia, and in return they were sending high value but low volume goods like incense, lapis lazuli, and things like that. So that kind of exchange was possible because you had this brief burst of increase in rainfall before it declined. But it's fascinating that it's kind of that. So this work we just published. In fact, it got accepted in Journal of Marine Archaeology last week. Adam is the lead author on this. We put together how that trade is possible because of environmental factors, which is this burst in monsoon winds. More recently, we have been looking at migration. So this is a paper that came out in 2017 in Science. Fascinating paper, how the population from Central Asia migrated into various parts of the world. And they are called the Amnayas, and their genetic signature is found in North Indian population. And so one of the fascinating questions is, they also started migrating right when the Indus was at its peak. And what we argue is that during the time when Indus was wetter, this region, the Central Asia, was dry. And because of that, the populations moved. And plus these population in Central Asia, they domesticated horses, and they also built chariots. They were the first to build chariots. So which means they could go further. And so that's why they could, from the Black Sea area, they could migrate. So this is simple reconstruction. Again, dark blue is dry, light blue is wet. And you can see right around the Indus is where the gradient is. So because of that, people moved. And so it's fascinating that climate also is in, so this is just the temperature signature during mid-Holocene. As expected, Northern Hemisphere is warm. And then it's the blue over India because of more rainfall, increased rainfall, the monsoon. So we also use this to reconstruct temperature and rainfall during Pliocene, which is 2 to 5 million years. And that paper came out in Weissich et al. 2019, paleoceanography. And again, you can see that in the Pliocene, the entire tropical Pacific was warmer. So this is what you're seeing, 0 to 5 and 4 million. So Indonesia is here. So again, your West Pacific warm pool was much warmer all the way into Central Pacific. So which means it was El Nino-like conditions perpetually. So less rain over Indonesia compared to modern, and also much less rain over India compared to modern. So we use these sediment cores. These are the sediment cores that had data going up to 5 million years past. And then we use similar techniques to reconstruct. And so here is the temperatures. As you can see, when you are at 5 million, there's very strong El Nino conditions. So which means less rainfall over the maritime continents, Indonesia, India, and notice that India had 50% reduced rainfall over entire India. This is all India rainfall. So again, interesting to see how things change. So
You have 5
summary.
minutes left.
Reconstruction, Pacific is during Holocene all the way up to 10,000 years, show gradual cooling back in time, La Nina-like conditions, and then more El Nino-like conditions in recent time. So based on the evidence, we argue that the suspect 2, which is ENSO or El Nino teleconnection, is more likely suspect rise and fall of Indus civilization, with probably some assistance from heating as well that gave more rain. But then once the land heating went away and the tropical week also got into more El Nino, then you had less rainfall over the Indus region. And implications for societies, always good to look at the past, learn from history, and we know that you can get these kind of dramatic shifts and sustained shifts that have serious impact on water, agriculture, migration, economy, not just over India, but also that entire region where, almost to 30% of the population of the world's population is living. So thank you very much. I'll stop there, and I will leave you with the slide. Happy to answer questions. I know I went way over time. Thank you very much for your invitation and for your warm welcome.
Okay. Thank you, Prof. Balaji, for your presentation, for your nice presentation about the climate change. In this case, it's monsoon related to change civilization in India. Please give big applause to Prof. Balaji. Okay, we move to the next presentation. The second presenter is Professor Rosli bin Umar from University Tun Hussein on Malaysia. Before Prof. Rosli make presentation, I would like to introduce you all about him. Professor Rosli got his PhD from University of Leicester in Autonomous System, his Master in Electrical Engineering from University of Technology Malaysia, his Bachelor in Electrical Engineering, Control and Instrumentation from University of Technology Malaysia. He is currently the Dean of the Faculty of Electrical and Electronics Engineering and also Associate Researcher, Faculty of Electrical and Electronics Engineering, Advanced Mechatronic Research Group in University Tun Hussein on Malaysia. His research interest is in autonomous system, control system, system identification, and robotics. Please welcome Prof. Rosli bin Umar. Time is yours.
Good morning. Can you hear me?
Yes,
I hope you can hear me.
Yes,
Very
yes.
clear, right? Okay. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. The respected Mr. Moderator, Dr. Engineer Puwarto Bekti Santos, STMT, thanks for your warm welcome to me. The Honorable Vice Chancellor, Professor Dr. Engineer Ahmad Sadiq, MSc Agriculture, if I'm not mistaken. The Honorable Dean of Faculty of Engineering, Dr. Engineer Suroso, STM Engineering. The respected fellow keynote speakers, Professor Balaji Rajagopalan, Associate Professor Yanto, Dr. Engineer Heru Dewanto, Professor David P. Whiteling, and Professor Silvio Ranise, professors, lecturers, and participants of the Third International Conference on Engineering, Technology, and Innovative Researchers 2021. Could you allow me to share my slide, please? Or you want to share on my behalf? Okay, now I can share this. I hope you can see my screen. Okay, this is actually my topic. The topic of my speech is development of visibility graph-based path planning algorithm for autonomous systems and I'm Rosli bin Omar, and this paper is co-authored by me and my PhD student Sanjoy Kumar Devnath. He's from Bangladesh, and we are from University Hussein of Malaysia, or we call it UTHM. And for your information, UTHM is one of the public universities. And in fact, in Malaysia, we have around 20 public universities, and we are number 15 in terms of timelines. We were the full-fledged university in 2007. In fact, we started earlier as a Polytechnic Staff Training Center, and later in 2007, we were upgraded into full-fledged university. And our university, I believe that most of you maybe don't have any idea where university is. Our university is, UTHM actually is located in Malaysia, and it is in the state of Johor. I mean, in Malaysia, we have around 14 states. In Indonesia, we call province. In Malaysia, we call state. It is equivalent. And Johor is one of the state in Malaysia. And Johor is actually located in the southern part of Johor, which is, I think, not far from Singapore. I mean, if you're driving a car from our university to Singapore, it's around 1.5 hours. And from our university to Kuala Lumpur, the capital of Malaysia, is around maybe three hours from our place to Kuala Lumpur. And our university has around 16,000 students, around 16 to 17. And the focus of our university is on technical and vocational education training, or we call it TVET. And currently we have around 7 faculties, and we have 3 engineering faculties, which is faculty of civil engineering, faculty of electrical electronic engineering, where I'm coming from, and lastly we have a faculty of mechanical and manufacturing engineering. So may I proceed to my slide, please? So this is the outline of my speech. I will introduce about path planning, and I will also tell you about the methods available for path planning. And then we go to visibility graph, which is my focus of my presentation. Then we will do a little bit review on real-time path planning. And later we will go into what we have developed so far. I mean, since I completed my PhD, I have been focusing on this topic until now. And lastly, we will try to evaluate the performance of the proposed path planning algorithms. So what is path planning? I don't know, maybe some of you knows about it. Some of you maybe don't know about it. Okay, path planning is a problem of determining a path for a vehicle in a properly defined environment from a starting point to a target point, such that the vehicle is free from collision with surrounding obstacles and its planned motion satisfies the vehicle's physical kinematic and constraint. What does it mean? That, I mean, you know, nowadays I think driverless car or self-driving car, or some people call autonomous car, is very important. I mean, very popular now. I think some of the companies like, you know, Tesla has autopilot, Mercedes-Benz has drive pilot, and also in China there is a company called Baidu. Maybe you know Baidu. Baidu also now very serious in developing autonomous car. So path planning is one of the requirements if you want to develop an autonomous car. And many more companies like, you know, Google also started in 2009 for autonomous car, and then later rebrand into Waymo in 2016, and now still developing the autonomous car. And what are the criteria for path planning? In fact, there are 3 criteria for path planning. The first one is computational time, which is one of the crucial criterion, where it is important because, you know, when you develop a path planning algorithm, you must consider the computation time. I mean, if the time taken is too long, it is, I mean, not good, you know. I mean, because in order to develop autonomous car, the car must be able to avoid obstacles immediately or instantly. So you must have a very good algorithm in order to produce autonomous vehicle. And secondly is a path length. This is also important because you don't want the car to go a very, very lengthy destination. But although you have a shorter one, okay? So this is very crucial where your algorithm should be able to produce the shortest path, or sometimes we call it optimal path. And lastly is completeness. What does it mean? It means that if there is a path, I mean, between point A and point B, your algorithm should be able to find it. Okay, I mean, if your algorithm able to find a path, a collision-free, meaning that the algorithm is complete. So there are two steps in path planning. The first one is representation of configuration space, or simply we call it C space. And the second one is graph search. Okay, there are many methods I will show you later of path planning. Okay, why path planning? So why path planning is we want to have a safe path, or sometimes we call it a collision-free path. Secondly, we want to have a shortest path in order to save energy of the car. We don't want to go very far away because we have a shorter one. And second, and the last one is we want to enhance the autonomy level of the autonomous car. Okay, this example, you want to go from point A to point B. Okay, starting point A and target point B. The starting point located at the right corner, okay, right upper corner, top corner, and the target point is located at the bottom left corner. So you have a lot of obstacles in there. You have, I think, around 7 obstacles. So how are you going from point A to point B? Okay, how are you going to go from point A to point B? So there are many methods I show you. Maybe method A will produce this path. The blue line is the path proposed by method, I don't know, maybe method 1. Okay, then there are another methods produce, the second path in brown color. And probably you have a third method. Okay, if you have many methods, if you have 10 methods, you will have 10 different paths. Okay, so the most important thing is how the path are fulfilling the 3 criteria that I mentioned before. Okay, so this is I put together all together. So you have 3 algorithms here, and we produce 3 paths. So now, as I told you, we want to have a path with the shortest distance. The time to calculate the path is shortest, and 3, the path is complete. So this is the review that we have done regarding the path planning methods. You can see path planning can be categorized under 3 categories. The first one is combinatorial, second one is sampling based, and third one biologically inspired method. If you see our method reality graph, it is located here, on the left hand side in the middle. So it is under combinatorial, and it uses C space to represent the path, and it is under the category of roadmap method. Okay, you can see a lot more methods there. For example, you can see a Voronoi diagram. Also, we have done some simulation regarding Voronoi diagram. Also, cell decomposition method. We have done also the simulation in our research, and also the potential field. In fact, one of my PhD students now focusing on potential fields, and she is at the final stage of her studies now. And also in sample based, there are many methods in path planning. For example, you have random, rapidly exploring random tree, RRT, and also you will have a method called probability roadmap, depth first search, breadth first search, Dijkstra algorithm, and best first search. And for information that visibility graph cannot stand alone as a path planning method. It must be combined with, we call it graph search algorithm. For example, like, A star, maybe Dijkstra algorithm, D star, dynamic A star, and many more graph search algorithms. Okay, in terms of biologically inspired method, we have a number of sub methods. For example, evolutionary algorithm, genetic algorithm, differential evaluation, and swarm intelligence, PSO or particle swarm optimization, and colony optimization, simulated annealing, ecological base. But I mean, in my research, I don't really focus on that biological inspired because sometimes when we read from the review, the time taken to plan the path is quite long. You know, I mean, it takes some time to plan the path. Okay, this is the comparison of the methods for path planning. So, for example, on the most left, we have RM. RM stand for roadmap method. Then we have CD method. CD stand for cell decomposition, and we have potential field method. If you see the VG on the top one, it is able to produce optimal path, but its computational time is not good actually. As such, it is not be able to apply in real time. Also, the memory also not good because it use a lot of memory for path planning, and also safety also not really good, but it is complete. You can see the rest of the method there. And for graph search method, we select Dijkstra algorithm because it can produce optimal path, and also it is safe and complete. Okay, for this is example of path planning using Dijkstra algorithm, where you can see the start bottom left and the target point, the goal is on the right hand side. This is how VG works, or visibility graph works. You know, you have some obstacles there in gray color, and you see the path is in the black. You can see that the path is very, very short. It is in fact the shortest among all the candidates. And then you can see this is what I said before, that VG is not good in computation time. It is very good in shortest path, and it is complete. Okay, you can see that the path now, the resulting path of VG is, I don't know, the cyan, not cyan, the magenta color or like pink color. And all the color in cyan actually is the path candidates. Okay, you can go maybe from here, maybe go to here, then go to here, go to there, and finally you will reach at the target point. But the path is not really short. Okay, so VG is able to produce the shortest path. As you can see here, that there are many edges here, or sometimes we call it the lines. That's what we call sometimes visibility lines. And here you see, because there are, I don't know, this around 20 obstacles here. So for 20 obstacles, there are around 3, 4, 8, 6 edges here. You can see here. If you can calculate it is around 3, 4, 8, 6 edges. And this is a formula we use to calculate the number of edges for this scenario. And as you can see here, that this is the number of edges versus the number of obstacles, the number of segments or edges, the number of obstacles. As you can see that as we increase the number of obstacles, the edges also will increase very abruptly. Okay, so VG is not really good for path planning in obstacle-rich environment. I mean, with environment with a lot of obstacles numbers. Okay, then this is the computation time of VG. I mean, we try to simulate environment with starting from 50 up to 300 obstacles in random environment. And for example, if you have 100 obstacles, the time taken to calculate the path is 20 seconds. 20 seconds is actually long. I mean, for a car to find a collision-free path, and it will go up to 160 seconds for obstacles, for environment with 300 obstacles. So this is really long. I mean, more than almost 3 minutes to complete a path, which is not viable for autonomous car. So what are our solution? What is our solution? Our solution is to propose a method, but still based on VG, because VG can, as I told you, can produce the shortest path. we propose two methods. The first one is we call equilateral space-oriented visibility graph, EASOVG, and secondly, we call it elliptical concave visibility graph, or ECOVG. Okay, this is the algorithm for the ECOVG, ESOVG, sorry. First, we create the baseline connecting PS and PT. PS is the starting point and PT is the target point. Then we identify a midpoint between PS and PT, and we create a midline passing through the midpoint and perpendicular to the baseline. And from each PS and PT, we create a pair of imaginary lines with an opening angle of P towards the midline. Okay, for opening angle, this is very crucial. You must determine the optimal or the best opening angle in order to get the shortest path and in order to get the shortest time possible for path planning. And we have done a lot of simulations. And finally, we found out that P starting with 15 is the best to produce the best path. And step number 5, we create an equilateral space S from the enclosed area by the 4 imaginary lines drawn in step 4. And next, we find obstacles OS located within the space. And for all nodes of O, we create an edges ES for each pair of nodes. And we check the visibility of each edge. And if there is collision, we add another edge into the cost matrix CM, and we repeat the step number 8. And finally, we will be able to find the part. I show you exactly what it is. Okay, this is actually the resulting space from the algorithm. And we coded this algorithm in MATLAB, and finally we will get the result of the path planning. You can see there is a midline, the midpoint, the P, or the row. The row is the open angle. And you can see the rest there. And this is the implementation of the path planning through simulation. We use MATLAB to simulate the path. You can see this is actually iterative IESOVG. Iterative means it will keep increasing. It will keep extending the size of the ESOVG until a collision-free path is found. For example, this one, you see here, since the opening angle is really, really small, so the path actually is not really inside the space. So we have to extend it until the path is really inside this area. Okay. Okay, this is the second method. We call it elliptical concave visibility graph, or ECOVG. I don't want to read each line, but the idea is we try to modify this shape, some we call like diamond shape, into this we call it elliptical shape, because in this shape you will have a better space here. So you don't have to extend it, I mean, many times, you know. And normally through the simulation we found out that the path can be found in the first iteration. You don't have to increase the size of the space. This example of the path planning using the ECOVG. Okay, so this is a very nice path. I think this is same scenario with this one. Same scenario, exactly the same location of obstacles, same number of obstacles, but you find this path is much faster because you don't have to increase the size of the region. The region is the borderline of the region is drawn in blue lines there. Okay, this is a comparison of the shape of the region. The left one is the ECOVG and the right one is the ESOVG. Okay, this is the comparison between the two methods. Okay, so you can see that ECOVG is much faster compared to ESOVG. For example, in 300 obstacles, ECOVG use around 5.69 seconds to find a collision-free path, which is quite good because in 300 is a lot of obstacles. Okay, while ESOVG found the path around 43.22 seconds. The improvement made by the ECOVG is around 86%. And in 250 obstacles, ECOVG found a path in 4.21 seconds, while ESOVG in 20.70 seconds, which is a lot of time, which is very long. And the improvement made by the ECOVG is around close to 80%. And in 200 obstacles, the ECOVG found the path in around 2.55 seconds, while ESOVG around 10.5, which is 75.71% improvement. And you can go through until the 30 obstacles, which is very fast. ESOVG can find the path around 0.05 seconds, while the ESOVG around 0.1 second, which is 50% improvement. Okay, as I told you before that, beside the competition time, the path length also very important. But it is surprisingly that even though ECOVG can produce a path much faster, but the path length still not really different from the from the ESOVG. You can see here, this is the graphical representation of the competition time. You can see the green one is the competition time of the IECOVG, while the red lines represent the competition time of the ESOVG. You can see that on the legends there, the top left of the graph, I stands for iteration. Why iteration? Because every time you couldn't find a path, I mean, every time the path collides with obstacle, you have to increase the size of the region in order to find a collision-free path. So that's why we call it iteration. And as I told you that this is the path length compared between both methods, IECOVG and IESOVG. As you can see that the path produced by IESOVG sometimes in fact is shorter than IESOVG, which is in 300 obstacles. The path is 1177.5 units, while the IESOVG is around 1184.8 units, and the improvement made is 0.66%. For your information, that we don't expect too much improvement for the path, because we assume IESOVG is already good enough in terms of path. It is not so far away from the conventional VG, because the conventional VG is the best. But since I told you the time taken to calculate the path is very long, so we try to propose a method to address the issue. And for 200 obstacles, the path length of IECOVG is around 11.7.5, same to the path produced by the IESOVG. And you can see until the bottom there, the 30 obstacle also, they have the same path length. So this is the comparison between the two methods. You can see that as the number of obstacles increase, the length produced by the IESOVG has slightly increased a little bit, very little, I mean. And this is the conclusion of my talk, that IECOVG has major advantages over IESOVG, as you can see from the tables and the graph, in finding a complete path in an obstacle environment. In this case, we demonstrated that we use up to 300 obstacles to compare both methods. And secondly, IESOVG model start with a small opening angle, which is the rho. And as I told you, the rho value must be carefully selected in order to have a very short time. Otherwise, you will have a very lengthy calculation, lengthy time, okay, very long time to calculate a collision-free path. And if several obstacles are located near the starting or target point, then the algorithm may fail or to find a path to complete a mission. This is also, I told you before, that since the opening is very narrow, okay, I mean near the starting and target point, so we try to improve the IESOVG by proposing a new method, which we call it IECOVG. An increase in the opening angle for IESOVG to find a path will allow it to cover a big area in sea space, which in turn may increase its computation time. Okay, so we must be careful, not too big, not too small, just nice. And this can be done through a lot of simulations. Then we can converge into one number, one value of the opening angle. And the next is the performance of IECOVG and IESOVG in terms of path length and completion time were compared and analyzed. And IESOVG was found to be relatively faster and capable to produce an optimal path than IESOVG in optical rich environment, as we have demonstrated before. In terms of computation time, IESOVG was better than IESOVG with 50.22 and 86.83 improvements. And however, the path length of both algorithms was almost identical. Actually, I have several results. Using different methods, as I told you. We also done the path planning using cell decomposition method. We also Voronoi diagram, also PRM or probability roadmap, and also potential fields. But I think for this talk, I only focus on VG. Maybe in the next ICETIR, maybe 2022 or 23, I can discuss another method regarding path planning, to share with you. I think that's all for my talk. Maybe I take less than 40 minutes. Thank you very much. Maybe there is Q&A, please, if you have. Thank you.
Thank you, Prof. Rosli Omar, for your interesting presentation. Professor Oman explained two algorithms for vehicle path planning with criteria of computational time, path, length, and completeness. We will give big applause to Professor Rosli Omar. Okay, we arrive at the last presentation for this keynote session. The next presenter is Pak Yanto, PhD. He got the PhD from Civil, Environmental, and Architectural Engineering, University of Colorado in 2016. Master of Science in Civil and Environmental Engineering from University of Michigan in 2011, and Bachelor of Engineering, Civil and Environmental Engineering, Gajah Mada University, Yogyakarta in 2003. Currently, he serves as Assistant Professor at Civil Engineering Department, Jenderal Sudirman University, Indonesia. His research interest is mainly in hydrology, especially in flood inundation, and also in statistics and stochastic related to hydrology. Please welcome Pak Yanto, PhD.
Thank you, Pak Purwanto. Terima kasih. Sini boleh. Ininya. Okay, thank you very much, Pak Purwanto, for the nice introduction. So, do we still have 25 minutes or 20 minutes? So I am the chair of this conference, and I think it should be wise. I need to control the time also. So I will try to finish my presentation at around 20 minutes. I hope I can do so. Today I'm going to talk about the incorporating global climate indices into flood design and what is the implication to societal resilience. So, Professor Balaji, he is my mentor. He is my supervisor in the University of Colorado. I learned a lot from him. So I think I'm not going to be what I am today without him. I will start my presentation. Please for the next slides. So the agenda for my presentation. The first, I will talk about the flood design and practice. And the second, I will try to explain the basic assumptions and the limitations. And we have alternative approach for that, and we will show the case study. Next, please. Ladies and gentlemen, we understand that everything we do make a risk. Everything we made create risk. And all of we've done in our life, I think it will generate risk. Of course, we have made a lot of changes on Earth. We built car, we cut trees, and then we burn coal and everything. And it has risk. And what kind of risk that we are facing today? So next, please. Oh, wait. I don't think this is the last version. Yang terakhir kayaknya bukan ini, Mas. Iya. Nope, nope. Bukan. I have the last version of my presentation though. Yeah, sorry. Yang PDF, Mas. Yang PDF, siap. Yes. Yang updated. Dapat, Mas. Good. Belum kelihatan. Okay, yeah. I'm sorry for some technical issues. So this is I think it's a survey by the World Economic Forum. So they have a survey about what kind of is in top of mind of people. And I think it's surprising because in the last 3 years, we saw that people think that climate change action and the extreme weather event and natural disaster is the top 3 in the risk that we are facing. So this is something interesting. Of course, this is taken before the COVID-19 pandemic, but like extreme weather event is it occurs every year. So I will talk about the extreme weather event and what is the consequence on human life. Next, please. This is some extreme events. So in the world, we have record snowfall in Madrid, and then there's some storms in UK, and also flooding in New South Wales, and flooding in Indonesia, and we have cyclone Seroja, Indonesia. 160 people died and 22,000 people evacuated, and floods in China. And overall, if we can see the effect of the extreme weather event, mostly in flood, if we can see in the Indonesia, next slide, please. Indonesia is a good, I think we have a good agency, BNPB, National Agency for Disaster Countermeasure. They update the data daily, and this is data from, I think, 2 days ago, August 30. It says we have 1,830 disasters, and 40% of them are floods. So this is something interesting, and I'm going to talk about more about the flood design. That is important. Why we'll talk about flood. And next slide, please. In terms of flood, one of mitigation measures that we can do, or adaptation measures we can do, is we have to have more storage to control flood. So to have dam, to have reservoir, to have like a well dam is very important. Even though some environmentalists says that we don't need more dam because it disrupt the environment, but really we need them for developing countries, because if we can see the data from the Food Agriculture Organization, the data says what is the storage capacity of them per inhabitant, per capita in a country. In United States, where they have more than 2,000 cubic meter per capita. In Brazil, they have more than 3,000. In China, around 572. India is less than that, 184. Malaysia is better. Malaysia have around 700 something cubic meter per capita, but Indonesia, we only have 90 cubic meter per capita. So looking at what the standard consumption of water for people, this number is very, very insufficient. So this is something that we need to think of about the water structure, and I think the government of Indonesia has also planned to build some more dams in the future, up to 61 dams. Next, please. So the water structure comes into different types, into different forms, like a dam. Dam is a high impervious barriers that we build on the river, and the purpose is to store water, to store water. And then the well dam is the same thing, but the purpose is to increase the water level. Also, we need drainage system for flood control. And all of them need something called design flood. So we have to perform flood design. This is a process of estimating the maximum flow allowed to pass a river. So the output is 2 years design flood. It can be 20 years design flood, it can be 25, 50, or 100 years. So this is something common in statistics when we compute the return level based on certain return periods. Please, next, please. So what is flood design in practice? What people do, particularly in Indonesia, that I observed. So usually they take a time series of stream flow, and then they compute the annual maximum stream flow. So take one number, the highest number at each year, and then, for example, if we have 20 years of data, and then fit the distribution of the extreme. It could be Campbell, it could be gamma, or it could be exponential log percent, and so on. So once we fit the distribution, and then we came with the accidents probability and take the return level for some example, that's I call 2 years design flood. Next. But this situation is not that ideal. So for example, if we have a new structure that we will build a new place, and then the stream flow data, we cannot get that. So the approach is to use the rainfall runoff model. So for that purpose, usually we use the rainfall data. We compute the annual maximum, the same thing, and then we fit the distribution. For the area, usually we compute with some method like averaging or polygon distribution or ICETIR and something else. With the distribution, we get the 2 years rainfall flood, and then with that we compute the design flood using the rainfall runoff model. So this rainfall runoff model usually based on some characteristics of the watershed, like the land cover, land use, and something like that. Next, please. Yes. So what is the basic assumption that they have in the simple runoff model? Next, please. So the first is we assume the linear relationship between the single rainfall events at daily time scale with the discharge, with the stream flow. And then the second, we take the average of the rainfall data of the watershed. So we take the mean value, And then the third is we use the historical data, assuming that the future will be the same with the past. So this is the basic assumption, and we understand that this is just a simplification of the hydrologic processes because hydrologic process is very complex in terms of components affecting the stream flow. Next, please. So I would like to give some basic hydrology. So hydrology usually relies on the hydrologic cycle. So we have evaporation, water come up from the sea, and then it condenses in the air, in the atmosphere, and then travel with the cloud, and then they drop down with precipitation, and then with that some are retained by the trees and others, and then some water will go into ground using infiltration, and then once the soil is saturated, and then the water will flow over land. It's called runoff, and then it will go to the river as stream flow. So we have, we have two parameters here: precipitation, that's P, and stream flow or runoff, which is Q. So at daily time scale, the hydrologic assume that if we have higher P, we will have a higher Q at daily time scale. Because once we have runoff, and they will go directly to the stream, to the river next. But something is not that same. So sometimes we have like storage before the overland flow get into the river. For example, maybe we have dam, we have reservoir, or maybe we have some natural ponds, lakes. So once if this happen, so when we have, for example, a high rainfall at daily time scale, and then it doesn't go directly to the river. It will retain by the ponds, by lakes, and then it will comes to the river on the next day. So we need like more than 1 day to make a high flow. So at this case, it is possible that we don't get the P will equal Q at daily time scale. So this is something that maybe no longer valid for the practice of design flood. Next, please. So this is from the conceptual aspect, but for the observation, so we observe stream flow in, this is Kalisapi sub-watershed, so small sub-watershed within the Sarayu River Basin. So we look at the stream flow, observation, and the rainfall of the watershed, and we found that which is marked with the blue box. That's not always that high flow correspond to high precipitation, which is confirm what the basic hydrology that I explained before. So this is something that we also need to consider when taking the simple runoff model, rainfall runoff model with daily time scale. Next, please. Another aspect that we need to think is that in the practice of flood design, they assume the future is the same as the past. But climate change is happening, and many studies prove that. So we can say that the extreme precipitation is intensifying. So this is a study from, I think, two different sources. The one is in the United States of America. So they have studied to compute how many areas experiencing the one-day precipitation events, extreme, in 48 states of the United States. And it says that from 1990, I think, the number or the area experiencing extreme daily precipitation event is increasing. Over the globe, there's also another study by Tabel 2020. This figure tells us about the percent of increase in extreme precipitation intensity. So for the A, it is for humid area, B is semi-humid, C for semi-arid, and D for arid areas. It tells us that many places in the world will experience the change in the extreme precipitation intensity. up to 10%. So this compare the projection of 2070 to 2099 compared to 1971 to 20. So like 1 year difference. But from these figures, we can see that yes, extreme precipitation is intensifying with the larger number. So we cannot design flood for the water structure with the historical data. We should use like some projection to make the water structure safe. Next, please. What is the alternative approach? Please, next. So we propose to use like four methods for flood design. First is to deal with the usage of mean values. So we use the principal component analysis. So this is like mathematical procedures that transfer a number of, so we have a lot of dimension in the data. So we want to reduce that. We want to find the principal component that explain the most variance of the data. It's called principal components. So basically in this, I think this method can be found anywhere in literature. I will not go into that deep. So the second is self-organizing map. So this is good method for clustering, for visualization. So this is based on the neural network algorithm, unsupervised. So in this method, for each input data, they have a neutron, that this neutron will find, will compute the discriminant function, and then once we get that, they will find the neutron that have a similar topology, and then they will group each other with the similar feature. This is important because I have different type of extreme. And the third is, it's called Bayesian dynamic linear model. So this is probabilistic time series. So I remember in linear equation, we have like equation y equal mx plus b with the same slope, but in PDLM, we have different slope, and so we have different intercept, because this is used, Monte Carlo Markov chain algorithm to estimate the number from the distribution, and then use the prior information to predict what is the slope intercept for the next time step. So this is good because we understand that the climate is some random events. And the fourth and the last is use non-stationary extreme value analysis. So this is, so we compute the extreme value, but adding the covariates to give more information about the underlying process. Next, please. So we perform this approach to Serayu supervision. This is this study area. We have Serayu. This is located in Central Java, Indonesia. I think there's more places, many places in the watershed with some extreme events like floods, landslide, and so on. And it happens every year, and many people are affected. So this is interesting for our study. Okay, this is the study area. We took one event, so I don't really remember the time when it happens, but in this place there was landslide, which caused 93 people killed and 150 houses damaged. And we observed with the rainfall data in the upstream rainfall station, we found that, oh yeah, that happens in December 12, 2014. And it is preceded by annual maximum rainfall, 3-day maximum rainfall, and 7-day maximum rainfall. So this is important to consider not only annual maximum, but also 3-day and 7-day maximum rainfall. Next, please. There's some characteristics of the study area. I think I can skip. Yeah, just to mention that we have 2 seasons, dry and wet season. I think the same thing for all of us live in around tropical area. Next, please. And yes, from the principal component analysis, we got the principal components. Usually the first components explain more variability, more variance than the second, because the algorithm will compute that in this order of significance. So the first will explain more, the second less, and less. And from the annual 3D and 7D, we got a good number because the first PC for the annual explains 77%, for the 3D 86%, and for 7D 99% of the variance. And we can see in the right hand side figure that there is an increasing trend for the annual 3D and 7D in terms of number. It means that the value of annual maximum is increasing from, I think, 1997 to 2018. So this is something that confirms what I said before, that the future is not the same as the past. The future is not the same as the historical data. Next, please. And using the space, self-organizing map, we can cluster the station data into 3 clusters. So in the left figure, so we have a fan graph. So the fan, the size of fan explain the number, the magnitude, and the color, I think, explain represent between annual, 3D, and 7D. And within cluster, there's also some configuration. For example, there are stations that between annual, 3D, and 7D maximum share the same contribution, but in other stations, only annual maximum have a large number, but mostly the extreme participant in these areas is built with the combination of annual 3Ds and 7Ds maximum rainfall. Next, please. So remember that in PDLM and NEVA, we introduced the non-synergy, where it's come from. So I think this has been explained very well by Professor Balaji. So there's 2 mechanisms that we need to consider in analyzing rainfall in Indonesia. First is called ITCZ, Intertropical Continental Zone. So this is the low pressure zone. For example, if you can see in January, there's low pressure over Indonesia, and the low pressure zone moves to the north at July. So imagine if you have low pressure, and then there will be a lot of winds coming, and then the winds will bring a lot of air moisture, and then it gives you more rain. So that's why we have more rainfall in January and less rainfall in July due to this ITGC pattern. And the second is, I think also Balaji has mentioned about this, but the Walker's equation with give you El Nino and La Nina. So this is also have a periodic. So for ITC, you have like once a year, but the El Nino, it was about 80 years once, but now it more intensive. So imagine that you have general ITCC and El Nino, La Nina condition. You have a lot of rainfall, and you have a lot of rainfall, you have a lot of flood, and so on. So it is possible that we have the combination of La Nina and July ITCC, or El Nino with January ITCC. Next, please. This is our study in 2016 with Balaji. So we identify the relationship with of the Indonesian rainfall with the global climate, with ENSO and IUD. So for the left figures, top, this is relationship with sea surface temperatures, the middle with the mean sea level pressure, and the bottom is the relationship of Indonesian rainfall with geopotential height at 500 millipar, and the right figure is the wind rate between, I think between, what's that, dry and wet season. So it says that Indonesian rainfall has strong relationship with the ENSO and IUD. ENSO is El Nino and Southern Ocean, and IUD is Indian Ocean Dipole. Next, please. And then, with that in mind, we developed the linear model using Bayesian dynamic linear model. So this figures tells us about three different extreme events. So annual maximum, 3-day maximum, and 7-day maximum. On each extreme events or extreme types, we have correlation with IOD and NINO or ENSO. The top is the intercept and the lower is the slope. So this is just linear regression model. Again, like you have y equal mx plus b, m is the slope, is the bottom part, and p is the intercept, is in the upper part. So in both three extremes, annual, 3D, and 7D, we can see that the slope is moving close to zero, but the intercept is moving higher away from zero. What does it mean? It means that we have m close to zero. It means the influence of ENSO and NINO in the extreme is smaller, but the intercept is higher. It means with the low anomaly, we can have extreme precipitation in Indonesia. And we can see in the, I think the recent years, we can see that we have like average extreme precipitation. And I think these figures confirm the real fact. Next, please. And then with ENSO and IOD, we developed the non-stationary extreme value analysis using covariate of ENSO and IOD for the annual maximum rainfall. And it says if we add the covariates into extreme value analysis, we get the higher return level for the same return period. It means if we design flood without considering the global climate, we will get lower value. What does it mean? It means that we will put people in the more vulnerable situation. So this is something important. If we want to make people, to put people in the more resilient situation, we should design the flood using non-stationary by adding the global climate indices. Next, please. And for summary, I just want to say 4 points. That first, the practical application of a simple rainfall runoff model that people use, usually in Indonesia, needs to be revisited. And the second, that potential use of different type of precipitation extreme, like annual, 3-day, and 7-day precipitation, needs to be considered. And the third is global climate indices are important for projecting future hydrology, and incorporating global climate indices into flood design will produce more resilient water shelter. It means that we will put people in more resilience. I think that's all of my talk today. Thank you for Pemantau. Thank you.
Your interesting presentation about the climate change and about the flood design should be consider the duration of precipitation and also should consider the climate change. We should give applause to Pak Yanto. Okay, I think we all have limited of time, but probably if you have any question, I invite the participant to ask your question. In the chat room, I think we have only one question to Professor Rosli Omar from Ms. Pendia Sri Aprilia. Yeah, he asked Prof. Rosli about how do autonomous vehicle distinguish live obstacle, for example, human crossing the road, and also that obstacle. It pretty heinous dilemmas. For example, if a couple of kids ran out in front of your vehicle, it may have to choose between surfing at the risk of your safety or staying in its path at the risk of theirs. Which way the EV will decide? This is the question to Prof. Rosli Omar.
Okay, thanks. Thanks, Mr. Chairman. Thanks also to the person who asked the question, Ms. Bandia Sri Aprilia. The question is, how do autonomous vehicles distinguish life obstacles? Normally, for example, Tesla Autopilot has around 8 cameras around the car that can cover around 360 degrees of the car, okay? And the range of the camera can go up to 250 meters. Okay, if let's say, I mean, in order, this camera, I think there is no camera that can detect human or dead obstacles. I mean, if you want to detect human, you have to embed, the thermal sensor so that it can detect human or maybe something that can move. I can have a motion, So, so this the way how we can distinguish between obstacle, human or dead obstacles. We will use the thermal sensors. And for the second question is, if a couple of kids run out in front of your vehicle, okay, which one the car will go? Either will hit the kid or you want to avoid the kid and the driver will have a risk of accident. To me, I think since I told you that for most of the autonomous cars, the range is quite good, around 250 meters. Okay, so if the car can detect the kids from far away, it might be possible for the car to stop in time before hitting the kid. But if the kid is too near, I think we have an option. I mean, either the kid will be hit or I don't know whether you will be able to brake in a very short time to avoid the kid. But as I told you that the role of path planning is to avoid obstacles where you the algorithm will try to find collision-free path. I mean, maybe it will calculate very fast, very quick in order to avoid obstacles, incoming obstacle. I mean, maybe the car in front, if the obstacle choose to select to avoid the children, the kids, and it might go to the other lane, the opposite lane, and it might have, the possibility to collide with the incoming vehicles. But if the vehicle, the algorithm can calculate fast enough, it can, dodge all the obstacles and finally come back to the lane. I think that's my answer for that question. Thank you.
Outside the schedule, 5 minutes outside 3 minutes. So you still have any question, you can send your question to our committee and then your question can be directly sent to our keynote speaker. So, so this is the end of our session, keynote speaker. Thank you very much to all three distinguished keynote speakers today for your knowledge and sharing to us. And also all the participants, please enjoy the rest of this conference. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
The certificates are awarded to the speakers in the first panel session. Professor Balaji Rajagopalan from University of Colorado Boulder, USA. Associate Professor Rosli Omar from Universitas Tun Hussein On, Malaysia. Assistant Professor Yanto, PhD, from Universitas Jenderal Sudirman, Indonesia. And now, for the next sessions, the participants are welcome to join the parallel session and then followed by break and lunch. For a parallel session, it will be shared in some virtual rooms. Please see your program book to know about session schedule. And also, we would like to remind our participants to join the second panel session at 13:30, and then followed by closing speech and announcement of conference word at 15:35. Thank you.
It begins from Kalibrantas expansion project in East Java, Indonesia. Since 1980, history justified that PT Brantas Abipraya were the first BUMN Karya that officially created by Indonesia government. Since that day, we were being inseparable part from Indonesia development. We learned, growing and transforming become the living company that surely proven can step up and facing the challenge. Well known with the holistic services construction company, which capable handling national strategic projects, currently PT Brantas Abipraya supported with 7 business units and 1 subsidiary that are productively and independently strengthen PT Brantas Abipraya position as one of the best construction company in the market. Abipraya Sumber Daya Air. Abipraya Gedung. Abipraya Infrastruktur. Abipraya Beton. Abipraya Alat. Abipraya Property. Abipraya Tol. And PT Brantas Energy. Abipraya, spirit for giving the best.